Rachel Wingfield. I'm the Creative Director at Luke PH, and we're presenting the Storm Laboratory at the V&A. So the Storm Laboratory is a new experimental piece that's looking at ephemeral architecture and how we can manipulate air and light and all this ephemeral phenomena into an architectural experience. The piece is it's an inflatable. This huge pneumatic form, so it's in the shape of a torus, essentially a donut, and then inside this torus we've got thousands and thousands of carbon-based polystyrene balls, essentially, that are being whipped into a frenzy with an array of fans that's mimicking weather systems and tornadoes, essentially. And you're able to actually go under the torus and stand in the centre and look around and view the garden. Also looking at weather data and how complex and difficult it is to model some of these systems. So the piece that we've made uses a lot of very analog, physical, tactile medium that's virtually impossible to model in any computer system. We found that an interesting tension here at the Digital Design Week. We've been given this opportunity to present here, and we've been told we could present an experiment. So it's a new body of work. We don't totally know where it's heading. We just know that we want to create a new form of architecture that's controlled and manipulated through air. So we want people to experience a space that's really turbulent, highly energetic, and think about some of our global weather systems, essentially.
My name is Lanfranco Ceti. I work as a professor, an artist and a curator. This is a piece that I have curated with the Museum of Contemporary Cuts, which is an organization that does alternative art forms. And the artist, she's coming from Australia with the support of the Australian Arts Council. The first piece is entitled For Cybernetic Strings, and it's a rather interesting piece because the people that are actually playing it, because they have their muscles disrupted by electric waves, they have to fight against those electric waves in order to be able to play. So the piece is dealing with the role of engineering and the contemporary electrics and electronic in disrupting the human body. And so how actually we are controlled and manipulated, and how our bodies twitch every time we receive an electric impulse. The second one instead is called Duty, and the artist Michaela Davis is someone that strongly deals with these issues that are related to power and control within contemporary society. So the second one, called Duty, obliges people to ring bells according to a particular soundtrack that she has written. And we decided to present the artworks here under the Elytra Filament Pavilion, because while we're looking at engineering, how engineering is redesigning our contemporary societies, we're not thinking about how engineering and electronics are actually changing the way in which we exist. And the artworks focus exactly on these issues.
I'm James Bott from Doubloon, a design consultancy I run with Henry Franks. We designed the V&A Samsung Digital Classroom. The The series of workshops is what Samsung and the V&A run, and it's for 16 to 19-year-olds. They come to learn about futures within the industry of the design and art world. It's to give them an insight into the industry that they potentially may not have. It's a classroom that can be constructed anywhere within the gallery. It's a mobile workstation that defines where the workshop is taking place, but then the public can kind of interact with it and weave in and out with easy exit and entranceways. It's made from light to try and inspire and excite the aura around the workshop. So the structure we've made is all made from 3D printed nylon joints that connect the tubes of light. So there's opal tube that goes into the joints, and each joint is bespoke to the area that it's in. There's a numbering system so that you can put it all together that's number and color coded, and each structure is independent of one another. So you can put up one structure if you're having a smaller workshop, or you can put up 3 to kind of create a more depth to the environment, or if you're doing a larger workshop.
I'm Grace Quintanilla. I'm the director of the Center for Digital Culture in Mexico City, and today we're exhibiting Ola Goldberg, which is a Goldberg machine, which is a mechanical machine that we've all seen various times in our lives. But this particular machine works triggered by sending a tweet with certain hashtags. So this is a piece of Internet of Things in which you make visible the impact, the physical impact of sending a like or tweeting a hashtag or whatever. So with this piece we want to make visible what apparently is invisible, and see how possible it is to affect the physical world just with digital interaction.
My name is Michiko, and I work with my art partner Michael Burton. So we are collaborating together and under the name of Burton Knitter. And we are showing here at the V&A our new piece called Landscape Within. And this project is basically looking at contaminated land and contaminated food we eat. We looked at our food, and unfortunately some of our foods are good at absorbing all these heavy metals. For example, rice is found as a really good hyper-accumulating plant for arsenic. We wanted to create a machine. We call it a digestive machine to digest out the heavy metals before we eat. So this part is where you feed the rice or food in, and then these tentacles moves and then crush and do our digestive system, basically slowly bringing the food down, digesting, and bring it into this bowl here. And in there is an engineered E. coli who is eating out the arsenic from our rice. After 4 or 5 hours, the process will be finished. So we drain down the water into the bottom bowl, and on top they've sent us this nano filter so that nanometals will be caught in the top part. So they basically, this bacteria automatically, as they absorb the metal, contaminating metals, they convert into nanometals, then we can use it as a useful product. And then we scoop out the rice, put into the sausage making machine, and then these bacteria can be modified. So we are planning to put the jellyfish DNA, so it's glow in the dark dining experience. So by the way, this project we are just launching with this event, so it's only 2 months on. So if you are interested in, please follow us. And we're gonna do a full launch next year in July.
Victoria, and I'm from King's College London from the physics department, and I'm a PhD student. And we're here on part of the Digital Design Week weekend, and also representing the Wheatstone Lab, which is a really cool project that we have at King's, which basically gets undergraduates really excited about science and doing experiments. My research is into biolasers, and this is a model of a laser I made, and I've made it completely out of silk. Why am I interested in lasers? So you must know that lasers are everywhere. They're in scanning devices, they're used in medicine. So we think we can use them for biosensing because they're an intense source of light. So we can use this intense source of light to start looking at molecules inside your body. So for example, if you have inflamed tissue on your skin, then the pH of that tissue is different, and that changes how our laser works. So we can detect that change. So this is a silk cocoon, and they're made by silkworms. And we use this material because it's biocompatible and it's biodegradable. We can put this into your body, and after 3, 4, 5 weeks, it will completely disappear with no toxic byproducts. So that's why we use this material to make our lasers, because we want to make a laser which can sense something relevant, but also that is not harmful for the body.
But what they can do, they can actually get the product.
So everyone's excited about 3D printers, but we thought, well, 2D printer, so we can program basically whatever we want, and it will do the design using a pen for us. So no more drawing, we can just now put it on the computer, feed it into the 2D printer, and have it print out whatever we want. So here we have a model of CERN, or the LHC. So what the LHC does, it accelerates protons really, really fast, at almost the speed of light. It uses really, really strong magnets, super cooled magnets, to get these particles to accelerate. And here's the model of that. So each of this coil acts as a magnet, and that's a magnetic ball. So they're turning on and off and accelerating the ball round and round and round. And this is exactly how the LHC works. And it will eventually collide these protons and look at what happens. So the idea is, from all of this energy, we can go back to the times of the Big Bang and try to understand exactly what happened and get more information about the beginning of everything.
So my name's Shelley James. I'm an artist and I work in glass. And I've had 6 months of a residency at the Wheatstone Lab at King's College, sponsored by the Crafts Council and the King's Cultural Institute. So for 6 months I've been working with the students in the department, developing some projects with them and for them, teaching them some techniques, but also finding that some of the things that I do shine a fresh light on some of the things that they do. And there's an area of their research which is to do with fluorescing what they call conjugated polymers, or quantum dots. So we've been playing with ways that we can use glass to express properties of those molecules in glass in different ways, whether it be in water or in other kinds of media. And that led to the development of a new technique for casting from 3D prints. So for example, one of the patterns that Ricardo's team works on is called a hyper-uniform pattern. And so this is cast in glass from a 3D print of a lattice that they generate using a mathematical formula. This is cast in glass and integrates what they call a whispering gallery, which is a way that they make different sizes of molecules and then shine a light through it and get the light to whiz round like a whispering gallery. One of the other effects they study is the way that molecules pack together. So I made some structures which actually physically do pack together. They are very precise sets of structures which pack together in the way that they play at the nanoscale level. So through this residency I've been developing some objects which help them to develop some objects which help the scientists to see their own work in a fresh light, but also help me to work in a different way as well.
My name is Matthew Pope. I'm a co-founder of a company called Cyanofeed. So we grow microalgae and cyanobacteria for the purpose of creating fish food. So conventionally, farmed fish are fed a diet of other fish, fish meal basically. So they go to the oceans, catch wild ocean prey fish, grind them up, and make fish pellets to feed the farmed fish. that's fine, but it's not very sustainable. So we want to use microalgae as an alternative protein source in the fish food. So the microalgae are microscopic photosynthetic organisms. We can grow them in fresh water like this. If you remove the water, then you're left with what we call wet biomass. So it's basically trillions and trillions of algae cells with the water removed. So it's like a big wet goo. Now we can dry this and combine it with a few other ingredients and put it through a pelleting machine, and we're left with the conventional fish pellets. So we'll feed these to farmed fish. So these farmed fish are usually bred in big nets in the ocean, and they require feeding 3 or 4 times a day. But the algae in the wet biomass has like 70% protein content, very nutritious, so it makes for an ideal fish food. But because we use the microalgae as the main protein source, and they just require sunlight and carbon dioxide as feed ingredients, it's completely renewable and sustainable. So we eliminate the unsustainability of the fish meal from previous fish foods.
Yeah, hi, I'm Philip. I'm here with Bentolab. Bentolab is a DNA analysis laboratory that's easy to use, affordable, and can be used by anyone. So Bentolab is essentially a laptop-sized DNA analysis laboratory. What we did was put the most essential equipment that you have in a big research lab, like a centrifuge, like a copying machine for DNA, a PCR machine, and other type of equipment, into one mobile box, so that it's much more affordable. It's also something you can take it into a camp or you can take it into a school. And yeah, it can be used by lots of different kinds of people for different kinds of projects.
I'm Rob Toulson from the University of Westminster. We're exhibiting an exhibit called Music Making is Greater Than or Equal to Computer Programming. Essentially, we're looking at a number of examples of sort of technical fusions between technology and music. We got a number of examples here, predominantly this robotic Internet of Things drum machine, which is essentially taking messages off an iPad on a web page, sending those messages to the cloud. The cloud is converting those to robotic control messages, and then they're performing those on the robot drum machine here. So people can basically program the machine, but actually, rather than it just make some electronic sound, it's creating some really physical acoustic sound. Essentially, people are making music. The great thing is that once they've done something random, they program it in a random way, they can then start to think about building patterns and actually going from being a novice programmer to someone that's actually designing some sound that sounds exactly how they want it to. So it's a really nice way of introducing people to the kind of organisation of music making.
So I'm Paul Shepherd from the University of Bath, and this is HAB, High Altitude Bioprospecting. And I'm here with Melissa Grant from the University of Birmingham and Olivia De Pea from the MRC, Medical Research Council. And we're scientists, and we're also here working with some artists, Anna Dimitriou, Alex May and Kira O'Reilly. And it's an art-science collaboration. What we did was we built a robot about that big, and we stuck it on top of a rocket. We launched it from the Nevada desert in the USA into the stratosphere. The reason we did that was to sample air in the stratosphere, looking for life, for biological life. Because if something can survive living in the stratosphere, it can survive very high levels of UV radiation. And we therefore want to know about it, because skin cancer is caused by high levels of UV, so we want to know about that to maybe develop ways of protecting us from it. Unfortunately, it was supposed to float down really gently on a parachute. The parachute didn't come out properly, so it came down like a rocket and embedded itself a meter into the ground. And what started off as a robot that big got crushed into a cube that big. And so the science that was in there was kind of lost as it got smashed onto the ground, and we had to dig it all out. We had syringes in there, and they were pulled with shape memory alloy springs to suck and blow the air through the system. And we had a little heater that heated the chemicals, and a detector to detect the bacteria. Since this happened, we've been continually working, having really good ideas about how we would do things better. We've been looking at ways of sterilisation, that we can sterilise it better either on the ground or in flight on the way up. We've also looked at the electronics and the control system, and these days we could do it much smaller, maybe on a tiny little Raspberry Pi thing rather than a big chunky board that we had. But we've got the 3D printer there because we've been looking at 3D printing the parts, that you can make them cheaply and very specifically and light, such that it can go up on the rocket and be stronger but lighter. He's got an air sampler there, so when we were in the desert we were sampling the desert air to look for contamination, and he's been sampling things in the V&A today so we can see the contamination that we've got as the people start walking through the corridor. So he's got lots of little things for people to try out and play with to show them the types of things we would do if we could do it again.